60s, the tabletops, all that stuff. No, I was scared to do that. I didn't want to do that.
My dad sits on the handlebars.
Yeah, I used to. We would go. There was a hill by my old house, and you would surf, where you put a foot on your seat and a foot on your handlebars, and you go down the hill. So we used to do stuff like that.
Did you ever fall?
Well, maybe once or twice. I don't know.
Did you wear a helmet?
I don't think they had helmets back then. So
they're required.
yeah, I know. Well, remember this is mid '80s, so we did a lot of stuff. Like we were just crazy. We used to build jumps and jump over things and all that. But what I'm getting at here, guys, is that the properties of the exponents that we've worked with before, all these same properties still hold true. When you have the same base and you're multiplying with different exponents, you add the exponents. It doesn't change if the bases have fractional exponents. All you have to be able to do is add 1/2 and 3/2. If I'm going to add 1/2 to 3/2, what do you get?
2.
2. What's 3 squared then?
9.
Oops. Okay.
Well,
So you wind up doing that. You just add your exponents. The rules for exponents don't change when they become fractional. That's what I'm getting at here. All these exponent rules that we've talked about in the past, they don't change at all. It's just a matter of getting accustomed to working with fractions. It's not that it's going to be horribly difficult. You just have to have common denominators to add them together. More often than not, you're going to be doing this if they're numerical, which I probably won't give you much of. Because numerical ones, you just put in your calculator. It's going to look like the stuff that you guys had on that last page in that worksheet where you had fractional exponents with variables. Okay. When you have power to power, remember you're multiplying them together. Power to power, if you have 4 to the 3/2 all squared, you take 3/2 times 2 and you get
6.
3.
3.
Oh,
Well, it's the same thing. I was right.
So you wind up with 4 cubed, and 4 cubed is 64. See how that's working the same exact way as it was in the past. The only thing that's different is that you have fractions. This is the one time the book does use the slashy fraction, and I absolutely hate it because they're just saving space. Okay, so just be careful with that.
Supposed to do slashy?
I don't like slashy fractions. Even when I do these, when I write these out, I try to write it as vertical as I possibly can, just to make it look a little bit cleaner. So you get the habit of it.
Okay.
I just don't like slashy fractions. That's just my own personal thing. When you have distributed property, it just means you have to distribute the exponent to both parts. It works the same way with fractions like we've said in the past. Oops, I have so many blocks in here, I didn't realize. So you've got your...
Wow.
It's all sorts of messed up today. I apologize. So if you're doing that, you have to take 1/2 power of both the 9 and the 4. It's just distributing through your exponents, okay? It's not a difficult concept to comprehend. It wasn't difficult when we did it before. It's just a matter of remembering how to use them, okay? When you have negative exponents are still not happy. We had a couple of problems like that the other day where you were able to flip things, put them in the denominator, put the denominator up to the numerator. It works the same way with negative rational exponents. We have fractional ones. They're still unhappy. They just move to numerators or they move to denominators depending on where they started from, all right? When we're dividing, we still play that game of war. Who's going to win? Numerator or denominator? That's when we subtract out. Those rules still apply. It's just with fractions, okay? Distributed property, fractional amount, it's the same thing. So basically what I keep trying to get at here is that none of these rules that we've done before have changed. They all work the same. It's just a matter of getting accustomed to seeing them written with fractions. Yes, ma'am? For where? This one?
Yeah.
You're distributing the 1/2 power to both terms. What's the square root of 9? What's 4? What's 3 times 2?
Okay.
Or, if you really wanted to be crazy, doesn't order of operations tell you to do parentheses first?
Okay, I got it.
You're going to get the same results. Okay? Yes, ma'am?
What are the answers to the bottom?
The bottom ones? All right. Who wins in a battle war? That's easy. It's 1/5. All right. Who wins in a battle war? 5/2 or 1/2?
5 halves.
What's 5 halves minus 1 half?
4 halves.
2. So what's 6 squared?
36.
All right. 8 over 27 to the third power, which means you're taking what of both the 8 and the 27?
The cube root.
What's the cube root of 8? Quick, what's the cube root of 8?
2.
You may enter.
What? Oh, I know.
That would have been me. I would have done it wrong. So I would
And the cube root of 27 is 3. All right. It's what we're looking at there. It's the same rules of everything that we've done in the past. The only thing that changes out is that there's a fraction exponent. Okay. All those properties are still the same. None of them have changed. And like I said, it's just gonna take a couple minutes to get used to seeing them as written in fractions. Okay. So let's do a few examples here. All right. I don't want to do numbers. Let's work with. So let's talk about properties of radicals then. Because not only are we working with properties of the exponents with that, remember how we can rewrite radicals, nth roots, to fractions as well. So I want to make sure you see how these fractional exponents work back and forth within radicals. Remember when you had the nth root stuff yesterday, and it was the nth root of A. That stuff is easy.
But it's not lucky at all. I know.
Okay, you had stuff like that. Remember when you're working with these things, again, you've worked with this before. When you simplified square roots by hand way back when, if you had to do something like the square root of 12, you broke that into 2 squares. Root 4, root 3. Okay? And the reason that you could do that was this product property. You had the same nth root, you just broke it into multiplication. All right? Split them apart. It allows you to simplify. This same process is going to allow you to simplify nth roots. It's going to allow you to simplify out cube roots, 4th roots, 5th roots, and so on. Stay with us! You almost fell out of your chair. You're lucky I saved you.
Come on, Ming. Keep my face. Stay in the
And it works the exact same way when you're dealing with division. When you're dividing out the entire fractional amount, you take the square root, the nth root of the numerator, nth root of denominator, and you simplify out that way. Those rules don't change. What this is going to allow us to be able to do are things like this. And notice I'm giving you numerical things. Numerical things would be stuff you could just substitute directly in your calculator and press enter. But some of these might not simplify out to be a perfectly, a nice integer. You'll have to write things into that simplified radical form, which means this is the style of stuff you'll have to crank out by hand. Yes, ma'am?
Are those two related to each other? Because I'm really confused.
They're not related to one another because that's a 4 and a 16. I mean, they're still even.
Okay, because I thought that one was the answer to that one.
Oh no, these are just 2 separate parts. I'm sorry. That's okay. If I'm looking at this here, what this is telling us is that you can work going this way or you can work going that way. So what's 4 times 16?
48.
64.
So now, what are 3 numbers you can multiply together to get 64?
4.
4. Okay? What that's allowing you to be able to do, and you might pick up on that. Notice how you have this can be rewritten as the cube root. God bless you. Well, not that, but couldn't that be rewritten as the cube root of 4 times the cube root of 4?
Yes.
Notice how you have 3 cube roots of 4?
So that makes 4.
Correct. All right. It's the same process as what you guys did when you worked with radicals, with just square roots. We'll put this one on a separate one. When you're working with division, do we have, in this case, the same nth root?
Yes.
Yeah.
I have the same nth root here, right? So could I rewrite this as one giant nth root of a fraction?
Yeah.
What's 162 divided by 2?
Is it 81?
It is 81. What's the cube root of 81?
3.
I'm sorry, what's the fourth root of 81?
3.
Because you can simplify it through. These, right here so you can see, these properties are similar to what you guys did when you just first learned how to work with just plain old boring radicals, square roots. The only thing that's changing up now is the fact that we're talking about nth roots. All right? Not so bad, I hope. All right. Good morning, Shuna. Hey, did you see this yet?
He's showing everyone.
Your headlight's much better. You can see it better. What Buckner did?
That's me too now.
Oh, that's good.
Yeah.
That's good. That'll be good, man. I can see this in the yearbook.
It's funny because I heard it's going to be for some reason.
Yeah, I can see that.
But yeah, it turned out to be a great shot.
And that young lady,
That's me.
I know.
She's a little too excited to do that.
You got some after you got done that. Mr. Murphy threw some to you.
Yeah, I was clean. You got me out.
No, he's very nice because if I was in that situation, I have picked up and paced you up.
I couldn't see it first, so that's why.
Did it get in your eye?
Coach, right?
When Rouse said his eyes were burning really bad. He took off his glasses. I got contacts, so it kind of helped, I guess, a little bit. But I had my eyes closed, but then obviously it just got in there. They were foggy for about 5 minutes.
But this is so runny. They
Yeah.
get
It was
you-
melting really
I
bad.
don't get how that's pie. This
I
is like
put
bunny cream on
on
the
the
plate.
It's
This one.
Why do they call it pie? They do it every time. It's
Because
tiny.
pie, like, it wouldn't really go in your face. Like, it didn't
No,
even
but if
have
you
to-
have a pie like
Banana cream.
banana cream or with
Yeah.
a lot of cream in it,
It'll
it
work.
actually work
Yeah.
much better.
Did you eat your real pie that you got?
Yeah, we had it the other night for
Is it
dessert.
What
Is it
kind
good?
was it?
Dutch apple.
That's a very good picture.
Yeah, it's really good.
Yeah.
You don't say it.
That should be the cover of the yearbook.
So, love it.
So we go back into the same idea to be able to simplify these things out.
Mr. Murphy?
Yes, sir.
Not in class yesterday. Did you talk to Mr. Murphy, what you were doing yesterday when you had a stop? You did. Hey, young lady. Hey, what did I just say?
Sorry, I didn't.
You're not paying attention.
I thought he was yelling at you guys. That's it.
I was just.
That's what happens. Did you talk to your teacher what happened yesterday in your class?
Did you guys order a pizza or something?
Were you behaving with the sub?
Yeah.
I think they're thinking someone else.
Yeah, I think we did. Yeah. Because I don't think we were doing anything.
I'll talk to you.
I'm so What is this about?
There you go.
What's the square root of 12? 2 root 3. Okay, good. Now, cube root 54. Here's where things start to get a little bit weird. When you start to simplify some of these out, when you're looking to do cube roots, trying to do those by hand, you're no longer looking for a perfect square. You're looking for a perfect cube. Now, when you're thinking about your perfect cubes, you've got 2 cube, 3 cube, 4 cube, 5 cube, and then they start to get really, really big. Okay? 2 cubed is 8, 27, 64,
125.
25. See how fast they climb up? More often than not, you're probably only going to be looking at 1 through 4 or 1 through 5. After that, they seem to get a little bit silly. I think 6 is 216. I don't know what 7 is. It ends in a 3. That's about all I know. But what happens here is you can break this down into a perfect cube root and something else. What's the perfect cube that goes into
27.
27?
And then there's 2
So I
in
can
there.
rewrite that as the cube root of 27 times the cube root of 2. Therefore, my simplified answer would be
3 cube root 2.
very good. That's the kind of things that we're looking at being able to do. Okay?
Wait, where'd you get the cube root 2?
What's 27 times 2? We're breaking them apart. It's the same exact process as it was when you're doing root 4 times root 3. Instead, we're working with cubes instead of squares.
Where'd you get the big 3 from?
What's the cube root of 27? There's where it came from. So, it also goes through when you're trying to simplify your radicals, or simplify square roots. When you're working with roots. Do you like to have square roots in denominators?
No.
No, that's bad. So we rewrite it as the 5th root of 3 times the 5th root of 4. Exactly. Just like we used to do with the rationalizing your denominators in the past. If you had a radical in the denominator, you multiplied it by itself to the top and bottom. You multiplied by that factor of 1. Remember that?
Yes.
So in this case, our factor of 1 would be multiplying top and bottom by the 5th root of 4. So I get the 5th root of 12 times, 5th root of 12 all over
1.
4. Now, is there a perfect 5th root that goes into 12?
No. I knew that one.
But the 5th root
One
of
does.
1 goes
One does.
Oh, okay, fancy pants. What's up? Now, every once in a while, you might come across one that'll work, okay? You might get something, I mean, 5th roots, obviously, you'd be looking at 2s, and it's not going to have 32. So it's the same process to what you guys used to do, with just different nth roots. Yes, ma'am?
So you can't put 12 and 4 in the
No, because this has an exponent, this one does not. I multiplied it by itself. This is a factor of 1. We did the exact same process if it was root 3 over root 4. We'd multiply the top and bottom by the square root of 4. Oops. We did root 12 over 4. Remember rationalizing like that? This is the same thing with just the nth root in front of it. I'm trying to show you guys it's the same thing you've done before. We're just having to write an extra number. Okay.
So is
Yes. Whereas in this case here, you could have simplified it further. Okay, yeah, it would be root 3 over 2. You could have gone further than that one. This one you can't go any further. And you're done. Same idea when you're adding and subtracting with the rational exponents. You have to have the same. In order to add and subtract like you did before with variables, you had to have the same base, same exponent to combine like terms. It's the same thing here. Okay? It works out to do the exact same stuff. Now, when I'm looking at this, excuse me, what I want you to do is think back when you had something that was 7 root 2 plus 2 root 2. It's 9 root 2. Why is it 9 root 2?
Because they are like terms.
They're like terms, okay? Now, isn't this the kind of the same idea as 7 5th root 6 plus 2 5th root 6?
Yeah.
So what would your answer be?
9 5th root 6.
9 5th root 6. But notice how they gave you in terms of a fractional exponent? What should you write it as?
A fractional.
That's all it is. If it gives you a fractional exponent to go with, put your answer as a fractional exponent. If it gives you in terms of an nth root, give me my answer in terms of an nth root. What's the answer?
so 9.
Your answer here is 9 times the 6 to the 1/5. And that's it. It's the same exact stuff with square roots as it is with this. Yeah.
Oh, I answered my own question.
I'm glad we had that conversation. When you have the cube root of 16 minus the cube root of 2, what do you get? Cube root of 14.
But you're allowed to do that.
Wait, no, you can't. Duh. You simplify this. You can't do that.
Many
Sorry,
root
brain
two.
farted.
Wait, don't you get like 3? No.
What's the cube? What is the perfect cube root that's hiding in the 16? The 8. And that's where you're getting at. So now in this case, you can rewrite this as the cube root of 8, cube root of 2, minus the cube root of 2.
So then you can get rid of the cube root of 2, right?
Hold on. What's the cube root of 8?
2.
2. So you have 2 cube root of 2 minus, can I put this in here and not change anything?
Yes. You could minus that.
So now what do you get?
1 root. Just root, cube root.
Cube root 2 is your answer. Everybody see that? It's the same process as to when you guys did radicals. Just regular old boring exponents when you're dealing with the fractions or with the square roots. All of those rules with square roots still apply to these. It doesn't change. Okay? It doesn't change at all. Don't even worry about this. There's a reason why your book and some of the questions that you're going to see, it says assume all variables are positive. A lot of times when you can take these nth roots and you work with things, you can get absolute value style problems because your signs can change. Your book alleviates that all the time by saying assume everything's positive. That's why you're going to see that. We're really short here. Oh well. Which means we can do this. There's some here. No, I don't do this. I'll do this.
Whoa. Get rid of the 2.
I'm going to cube root something with a variable and a number. You're going to take the cube root of both parts. And you're going to be very, very pleasantly surprised at how easy this works. Ooh.
I hope so.
All right, what's the cube root of 125? 5. How many times does 3 go into 6?
2.
Any left over?
No.
Yes!
I like that.
Why?
Seriously? Seriously? That is like, wow. Bing is half
What does half power mean? Square root, okay? What's the square root of 9?
3.
It's 3.
What's the square root of, what's power to power, what do?
You add, multiply them.
What's 2 times a half?
What?
Yeah, you totally 5.
Power to power, what do? Multiply.
Could you just find the
What's 2
square root?
times 1 half?
What you do?
1. What's half, or what's 10 times 1 half?
5.
Why do they always put U and V by a square root?
I don't know, it's annoying, isn't it?
Yeah, that's right.
Okay.
Because it goes T, U, V.
Oh
no.
4th root of x to the 4th, y to the 8th. You're going to find out the nth root ones are a lot faster. How many times does 4 go to 4?
1.
Any left over?
No.
4 goes to 8, how many times?
You get rid of the 3 with 2.
Let me give you, I don't know if I'll be able to go as far as I wanted to. Let me give you a few of these to try out. I know I'm running late.
I have to do literally mean like
Yeah, I will.
Blindfold.
All right.
Well, she says that she'll arrive on the 20th. But I'm not sure what she's doing because she can go to grandma's house.
Do those. Those are all numerical ones. Try not to do with the calculator. We'll go back to work with variables tomorrow. Okay? We'll continue variable stuff tomorrow. All right. Go with that one to start. We'll go off of that. Excuse me.
Actually, you see one of the
Okay,
I do that.